Be the longest Cthulhu game of our lives.
It'd just be guessing.
They have like the time.
Actually, probably Braden would be the winner because he could just.
Yeah, because my guessing is 1 point.
Yeah.
Okay, quick review of how you play Jeopardy. You play Jeopardy by answering questions in the form of a question. Okay, good.
Well, answering answers in the form of
Your answers are in the form of a question. There you go.
Well,
Stay with things.
alright, now. Sure, it's like this again.
Okay, I'm Alex Trebek, and I'm here to teach you some calculus. So, first question, first Jeopardy question. The category is antiderivatives.
What the?
Oh,
Oh, it's math?
Oh, yeah, how about that? So the first question is,
Can I pick a different category?
you cannot.
Wait, we didn't pick the category though. Where's the
Yeah, I picked it for you. This is not a democracy. Don't kid yourself.
This is like the
Step.
North Korean version of Jeopardy.
They're doing math lyrics.
No.
It's like 6 foot, 7 foot, 8 foot, what? And it's like if
Boom.
you those lyrics, it's so funny. I laugh so hard every single time I watch it.
Okay, start thinking.
When we only have it.
Hit the buzzer. Oh,
That was
okay, it was a dead tie. Odd or even?
even.
Odd.
It's even.
God.
Oh,
I
my.
know it.
Odd because 21 and
No, I saw him go
two.
two.
Oh,
Say cheater.
I did go two. Okay, so
Figured 21.
what's the answer?
What is x cubed?
Yeah, what is execute?
Okay.
What is it?
That was
Or what is the
if we
derivative
get a
of
hard
x
one.
cubed?
Oh.
What is x cubed? It's fine.
Derivative of execute.
Okay. Well, no. Okay. Yeah, you're right.
To properly word that.
I should have said maybe the derivative of this function is 3x squared, and the answer is x cubed. Okay. What you just did is an antiderivative. That's all it is.
Whoa.
That's the process. It's just undifferentiating something.
Alright,
That's
let's
it.
leave now.
Okay.
State wins.
So yeah, you're done. You're done. You can graduate.
You should graduate.
Okay. Do you guys have? I'll give you a chance to redeem yourselves though. Can you give me another answer that also works to tie it up?
Oh,
I can.
let's see.
What do you do?
I feel like I should be able to do this. I don't know.
You got a large set to choose from. There are an infinite number of possible answers.
Can I go? Well, can I double Jeopardy it real
You,
quick?
you might be able to.
Is it? It's like a. Oh,
Couldn't you just
oh my god.
You might be able to.
add a constant?
Yeah, you have x cubed plus 1.
There you go. Woo! All right, you got it.
We're overthinking that way.
Yeah, I was like, what do you guys do?
So we could have also
I was like, get the 3.
we could have also said x cubed plus 1, couldn't we? Right? Yeah, that works.
Okay.
Okay, so then
Yeah, I was trying to change the exponent. I was like,
let's turn this into something real then, right? So this is just calculus Jeopardy. Antiderivatives is literally just playing calculus Jeopardy. That's what it is, right? So what we could say here though is if f of x equals 3x squared, then capital F is usually how we do this. Capital F of x equals x cubed is n antiderivative of f of x, right? So is x cubed plus 1. Well, that's going to be pretty annoying to just have to write down an infinite number of different solutions.
x cubed plus k.
And so we could say something like instead, we could say that, well, how about if we say, we'll change this a little bit. We'll say that we'll get a better answer. We'll call it g of x. And g of x is equal to x cubed plus c.
Oh, let's see.
Okay?
Wait, I thought k was the
Constant is spelled with a C.
Well, yeah,
You
but no,
stupid.
in physics. Okay.
A lot of times we do, but in calculus you always
Okay.
use a c.
Yeah.
It's always a c.
But
Wait,
physics has a
Some
k.
C
so
for
I think-
constant.
We're just too dumb.
I thought we would use
But-
K for constant.
No, physics has a k.
Because
So
I
that's
thought
where that came
that
from.
It does.
That's
A lot of
ancient,
times,
right?
It's a different kind of.
Okay.
Point well taken. A lot of times if you have like a constant of proportionality, we typically call lowercase k, right? But when we're doing
At least
The-
I'm matching.
the constant of differentiation, right?
Okay.
When we're writing an antiderivative, we always attach this constant at the end, and we make it a capital C. Okay, and that's just the way it's done always. Why are they different? Just because that way you kind of know. I mean, you can see. Sometimes we might do problems, and we will, where we're going to have both a k and a c in there, where the k is a constant of proportionality, and the c is the calculus constant we get along with the antiderivative, for example. When we get up to logs and exponentials, then we'll start mixing those constants up in weird ways. Okay, so this is what we would call then. This is literally the general solution of the differential equation. Of the differential equation, y equals, or f of x equals, we could write it either way. Let's just write it as, f of x equals 3x squared. Okay, that's the solution. Okay, or f prime of x, sorry. The derivative of this is equal to 3x squared. Well, what's the function? What's a differential equation? Differential equation is just an equation involving a derivative that we have to undo. Okay, so if we start off with f prime of x equals 3x squared, that's equivalent to the calculus Jeopardy question. The derivative is 3x squared. F prime equals 3x squared. What's the answer? Play calculus Jeopardy and
It's our
see.
next test, but I like this. Let's see.
You like this? Yeah, it's coming up. Yeah.
He's just tricking us.
Where
into
you
learning.
take-
He'll probably get it wrong.
Where it takes you 5 minutes to figure out with, +1.
I mean, when I went to do the derivative the first time, for some reason I was like x to the 6th. I tried to multiply them. It's not good.
Okay, so let's start with another differential equation.
Okay.
Or diffie q, what you'll call it in college, diffie q's. So y prime equals 2. Go. I want the general solution to that differential equation. What is it?
2x plus c.
2x plus c.
What is 2x plus c?
Yeah.
Well,
So the solution to this is going to be y equals 2x plus c. Good. Okay. That's the general solution, right? Okay, let's look at what that looks like for different values of c, and I want you to see something here. So if we pull up, I'll pull up Desmos, how about? And let's just graph a bunch of these. So we've got 2x,
plus 1.
we've got 2x plus 1, we've got 2x plus 2, we got 2x minus 1,
Oh my gosh.
we got 2x minus 2, and what do you notice?
They have the same slope.
It's a ring.
Yeah, this is what we would call a family of curves. Okay, the solution, isn't that nice? The solution is a family of curves. There's an infinite number of curves, and each one of those we would call a trajectory of the family. Okay, so the solution represents all of the infinite family of curves that look like that correspond to lines with a slope of 2, right? Okay, but that's the general solution. What if we impose some initial conditions, initial conditions I'll explain why. That's a word that gets attached to these all the time, these kinds of problems, and it's not a great word. A better word is particular conditions. I'm going to, and I'll tell you why that happens in a second. We're going to attach the constraint here that, how about something like, we're going to attach the constraint that the solution has to pass through the point 0, 2. Or in other words, x equals 0 when y equals 2.
What is y equals 2x plus 2?
Okay, that would be the answer, wouldn't it? And we can see that if we go to these graphs, which one of these curves passes through the point 0, 2? Well, that was the green one, right?
Yeah.
So that's the winner, right? That's what we would say then is the particular solution. That's the particular solution that matches that constraint, okay? So we'd end up with y equals 2x plus 2. Okay, we got that pretty easily because that was a pretty simple family of curves. But how could we have done that algebraically?
Could have plugged in y for 2 and then solved for c.
Okay, good. We could have plugged in
The
0 for x and 2 for y and solved for c, right? If we plug in the initial or the particular conditions, then we end up with solving for the particular value of the constant, right? That corresponds to that one trajectory, right? Okay, let's try another one. Okay, so let's try, how about, make this a little trickier. Let's do something like, what if we want to solve y prime equals cosine x? I want the general solution to that.
What's your guess' favorite?
What do you think?
What is sine x?
Yes, it would. It would. The answer would be y equals sine x plus c. And how could you check your answer?
Did you not say?
Take the derivative, right? So the derivative of sine x is cosine x, the derivative of c is 0, right? Okay. So for simple ones, that's going to work. But you can kind of see here that we did some complicated derivatives too, right? So we're going to do some correspondingly complicated antiderivatives. And so we're going to evolve like a parallel line of reasoning here. We came up with some rules that we could use to solve. If we followed the rules, we could solve fairly complex derivatives by just, if we might have had a quotient rule. We might have had embedded in a quotient rule, maybe we had the chain rule or something, right? Same kind of thing we can do for antiderivatives. We'll call them integrals later. Antiderivatives, but the bad news is it gets more complicated because the rules, when you're working backwards like this, it's harder to make the rules apply. Okay, it's a little more complicated process, but we'll practice that. For now, though, let's add let's formalize this a little bit. So if we want to go from something like this, so if we go from dy dx equals f of x, right? We want to get that to the answer y equals some antiderivative that we'll call capital F of x plus a constant. What's the process look like that we use to do that? Well, it's not an accident that we just talked about differentials because that plays a part here. What we can do is we could rewrite this in differential form. So what's that going to look like? dy equals, okay, is going to equal, well, we just call this f of x, right? This is, so whatever that function is, times d of x, right? Okay, and so we want to undo that, right? Well, how do we do that? If we want to undo that process, there must be some symbol to represent undifferentiating, right? The symbol for undifferentiating is the integral symbol, right? So this is the symbol that represents reversing differentiation. So what is gonna be the antiderivative of the derivative of y? It's gonna be y plus some constant, call it C1, right? Agree? Okay, what's on the other side? Well, on the other side, we've got the antiderivative of f of x dx, which is the calculus jeopardy part. Okay? So when all is said and done, we want to be able to undo this, we want to be able to unlock this derivative. Well, like we've looked at some examples. We did a cosine, we did a 3x squared, could have been f of x, we did 2, right, was f of x one time. Each time you guys were successful, you were able to come up with what is the function that reversed that differentiation process, right? And we'll add some rules to that eventually, but for now, this is where the calculus jeopardy comes in. And we just end up getting some answer, which is gonna be, we're gonna call f of x, which is the antiderivative of f of x, right? Plus some constant, call it C2, and then we'll just combine all the constants in one. So effectively, you can just forget about that one. Because ultimately, we're just gonna put one constant at the end of this, which is the constant, right? It represents any possible constant. So then this looks like, go away. So this looks like y equals the antiderivative of f of x dx, and the solution to that is going to be in the form the antiderivative of f of x plus c, right? And the way we define this then is the antiderivative. Capital F of x is the antiderivative of f of x, which is calculus jeopardy stuff, right? Okay. We call this the constant of integration. Because really this process will we'll come to call it integration, okay? Integration is the opposite of differentiation, okay?
So is it possible for there to be a function where its derivative is the same, essentially the function?
It actually is possible. You know, there's one function that we'll get to eventually where that's the case.
Other than like y equals 0?
No, y equals 0 doesn't work.
Or x equals 0?
X equals 0
Because
doesn't
that'd
work.
just be a straightforward sum to y, wouldn't it?
You're right, but the derivative of any constant could be 0, right? So the answer is 0 is not, so C would be your answer. And the antiderivative of C is not C, it's Cx. Okay, so, but there is one function, which, we'll get to it later, it's actually the exponential function, e to the x. The derivative of e to the x is e to the x. Yeah, which is weird.
E to the x?
Yeah.
Yeah.
That 2.78 or
Yep.
whatever?
And so this is, just to finish this up, this is what we would call the integral sign. Or the integral symbol, I guess we should say. Integral symbol. And what that is, and this is going to be weird that we would make it this is a lowercase Greek sigma. You've seen sigmas before. An uppercase Greek sigma looks like this. What did you use that for? Sums. Aha, interesting. So there's going to be a relationship there, an important relationship that we'll uncover in the next week. Okay, there's a reason that we picked a lowercase sigma. Okay, so then that's one way to write this relationship. Okay, there's another way we could do it. We'll show the inverse nature. So if we reverse this thing, if we were to take the derivative of this antiderivative, what should we get? let me say that again.
If you take the derivative of the antiderivative, you get the back.
It should give me the same thing back.
Yeah.
So if I take the derivative of the antiderivative, that I should get the same thing back. If I take the, I don't want to say this. I want to show you a relationship that's important here. So this is true. Does that make sense?
There's the numbers.
Okay.
There's one number.
So the derivative of the antiderivative, right?
It's a prime.
These processes have to undo each other, don't they? Right? If I'm going to take the antiderivative of the derivative of the antiderivative, then that has to undo that whole process. They are inverse processes in the same way that a cube root and a cube function are inverses. They undo each other, right? Okay, that's equivalent to saying something like this. We could also say if we start with f of x and we take the integral, and by the way, notice that the integral always has to include two parts. It includes the symbol, but there's also going to be this variable of integration, which looks like the dx part of the differential, right? So this part in the middle, we actually call the integrand. And that's the part that we're actually doing all the work on, right? That's the function we're playing calculus Jeopardy with, right? Well, how could I show here, how could I get an answer back? What would I have to do to this side to get back an answer of just plain old f of x? If I'm going to anti-differentiate this, what could I do to the antiderivative to undo the antiderivative? Take the derivative, yeah. Right? If I differentiate the antiderivative, they cancel because they're opposite processes, right? And I end up with just plain old f of x. Whatever the integrand was, whatever was in the heart of that integral, that's the function that we're trying to undo, right? Well, if we undo the undoing it, we just get that function back.
So, with that one and the other one that you have both of the arrows pointing at, it seems like you're just ignoring the dx, effectively.
Well, we kind of are, because let's look at an example of a problem. What do you think the answer to this is? What's the antiderivative of 3x squared dx? Plus c, right? Did we even need the dx? No, we didn't. We're just finding the antiderivative of 3x squared. What do I take the derivative of to get that, right? So you, in a sense, you are. The integrand is what you're trying to undo. The dx is really just there for reasons that will become more clear later when we explore what the sum part of this process is. The reason it's a sigma is because it actually works to sum some important things, right? So that's kind of why that is there, right? But really, this is the part that you always are focusing on. You can almost consider, in fact you do, when you start doing integrals, you really just consider these two parts to just be kind of brackets. I mean, those are just what's bracketing the integrand, which is what you're trying to undo, like calculus Jeopardy. Okay? Let's try something like this. Let's move on to a little harder differential equation. So let's try to solve this. What if we've got, I wanted to do number 16. We're in section 4.1, by the way. Yeah, so something like this. So x squared here. Okay, so we're gonna solve that integral, right? So we're essentially solving a differential equation. We want to know what can we differentiate to get this result, right? How do you think we would approach this? What do you mean by starting at the beginning? I mean, there is.
Start at the x squared.
Okay, yeah. Think back to how we differentiated things. We always were able to differentiate problems term by term, right? If we had a whole bunch of terms, like in a polynomial, we could just take the derivative of each term separately, right? So doesn't it make sense if we reverse that process, that term by termness would stay the same, right? That each one of these separate terms must have come from the derivative of a separate term, right? So therefore, we can integrate or anti-differentiate term by term as well. So we could think about this as being three separate antiderivatives and just deal with them individually, right? So what's going to be the antiderivative of x squared? Okay, that's going to be x cubed over 3, we'll say. Negative 2x,
X squared,
and then 3.
3x,
Okay, now what do I need to do?
plus
Yeah, each one of those incorporated some little constant. We'll just lump all the constants together into one big constant, right? So do you have to always think about it in terms of a bunch of no, you don't. You always just know when you take the antiderivative of some integrand, you got to include that plus c. It's actually a very mechanical process. You just have to account for the possibility of another constant there, right? Okay, let's try a little harder one still. How about something like this? Yikes.
Oh, okay.
Plus root x of the second bunch.
Mm-hmm. Okay, what might be helpful to do here, just like within it with derivatives, to those radicals? Okay, write them as rational exponents. Okay, so we could write this as the antiderivative of x to the 1/2 plus 1/2 x to the
negative 1.
-1/2 dx, right? And now we got to kind of think in reverse here. Pretty soon we'll have some rules that will be able to make this a lot easier. But for now, what's going to be the antiderivative of that one? The derivative of what is x to the 1/2? What's the power going to be of x? 3/2. Okay, so you know you're going to get an x to the 3/2, but if I differentiate that, I'd have to have a 2/3 up front, wouldn't I? Because when I differentiate this, I've got to be able to cancel that 3/2 because it doesn't show up here, right? You get the idea? Now what about over here? Let's see, the derivative of x to the -1/2 is what?
X squared.
Okay, and then let's see, I have a 1/2 there, so I don't have to do anything, do I? Right?
Plus c.
Plus c, and we're done.
That's gonna be the new gravity.
What's that?
Like,
Jeopardy?
like in physics, whenever you ask, okay, what forces are affecting? Gravity, normal force.
Uh-huh.
Gravity, normal force.
Yeah, so plus c is the new,
That's
that's the new gravity, yeah.
Yeah. There's this.
All right, so I'll put up an assignment. We'll talk more about this on Monday. Take tomorrow off. You guys been doing a